Look at the sheer mass of water held back by a modern concrete dam. Millions of tons of fluid sit perfectly still, holding an immense amount of latent potential energy. The engineering challenge is figuring out how to translate this static geographical feature into active electrical grid power. We execute this through a continuous sequence of energy conversion. The potential hydraulic energy of the water transforms into kinetic energy, which is then extracted as mechanical energy and finally converted into electrical energy by a generator. This diagram illustrates the overarching layout of the plant. 5 macroscopic components make this conversion possible: reservoir, dam, penstock, turbine, and powerhouse. Fluid accelerates from the intake, rushes down the pressurized penstock, strikes the turbine housing, and exits. The dam provides the necessary elevation and storage. The transition to rotational power is concentrated entirely within the turbine runner at the base. As water plunges down the interior of the penstock pipe, its pressure and velocity increase dramatically. Waiting at the bottom is the hydraulic turbine. This is the exact mechanical device responsible for extracting hydraulic energy from the fluid and converting it into rotational shaft work. The French engineer J.V. Poncelet first formalized the mathematical idea of extracting mechanical work directly from fluid momentum, but a single baseline concept could not accommodate the extreme variations in fluid pressure and velocity found in different rivers and mountains. Therefore, this foundational idea required intense engineering specialization. Over the next century, engineers L.A. Pelton, J.B. Francis, and Victor Kaplan developed the distinct, highly specialized turbine architectures we use today. These designs represent distinct mechanical branches, each developed to solve unique hydraulic and pressure requirements. Turbines cannot be swapped universally. A design optimized to handle the extreme pressure of a mountain range will fail to turn on a flat, slow-moving river. Engineers use 5 rigorous criteria to select a hydraulic turbine: the available head and quantity of water, the hydraulic action of the fluid, the direction of flow through the runner, the turbine's specific speed, and the disposition of its shaft. The most critical variable is head, the available elevation drop between the water source and the turbine, which dictates both the water's pressure and its velocity potential. This diagram illustrates 3 elevation profiles. Panel A shows a low head setup under 45 meters using Kaplan turbines. Panel B demonstrates medium head installations, 45 to 250 meters, where Francis turbines operate. Panel C shows a high head drop over 250 meters, requiring a Pelton turbine. The landscape dictates the fluid's energy density. Engineers must adapt entirely different physical architectures to successfully extract that specific energy profile. Beyond geography, we categorize turbines by their hydraulic action. This defines exactly how the fluid imparts force onto the metal blades. This schematic demonstrates an impulse turbine. Here, a high-velocity kinetic jet of water strikes the buckets of the runner in an open environment, operating entirely at standard atmospheric pressure. The geometry of the bucket splits and reverses the jet's direction, extracting nearly all of its momentum and transferring it directly to the shaft. Contrast this with a reaction turbine in cross-section. The runner is completely submerged in a pressurized casing, extracting energy from both fluid pressure and kinetic velocity. The outer spiral casing and precisely angled guide vanes direct the pressurized fluid into the rotating blades.
Impulse relies on raw, high-speed kinetic strikes in open air. Reaction is a fully sealed, pressurized puzzle where energy transfers to the runner as the fluid expands and drops in pressure. We also classify turbines by the specific geometric path the water takes through the runner housing. This illustration details internal paths. Diagram A shows tangential flow, striking the runner's outer edge. Diagram B shows radial flow, moving toward the center. Diagram C displays axial flow, moving parallel to the shaft. Mixed flow enters radially and exits axially to maximize contact. All these physical characteristics roll up into a single mathematical concept called specific speed. This is a theoretical metric that calculates the speed of a geometrically similar turbine scaled to produce 1 unit of power under 1 unit of head. This table maps specific speed ranges. Pelton turbines sit low at 8 to 30. Francis turbines occupy 50 to 250. and Kaplan turbines range from 250 to 850. These speeds dictate orientation. Pelton turbines require horizontal shafts, while Francis and Kaplan typically mount vertically. Specific speed acts as the genetic code of the turbine. Calculating it tells an engineer exactly what shape, size, and orientation is required for a given site. Moving from theoretical design to thermodynamic reality means confronting a strict physics constraint. No system is perfect, and energy is constantly siphoned away. This schematic maps the energy loss. The elevation difference between the reservoir surface and tail race is the gross head, Hg. However, the friction of water scraping against the penstock pipe creates a frictional head loss, reducing the actual pressure reaching the turbine. Net head equals gross head minus this frictional head. That friction factor is calculated using the Darcy-Weisbach equation, accounting for the pipe's length, diameter, and the fluid's velocity. The turbine never has access to the full theoretical potential of the reservoir. The concrete and steel architecture of the dam charges an energy tax before a single drop of water even touches the blades. Once the water reaches the powerhouse, energy escapes through nozzle friction, eddies, and bypassing the runner. First is volumetric efficiency, the ratio of water striking the blades versus total water supplied. Next is hydraulic efficiency. This compares the power developed by the runner against the actual power supplied to it by the fluid, accounting for blade friction and turbulence. Then we measure mechanical efficiency, which compares the final shaft output to the runner output, subtracting the energy lost to the physical friction of heavy steel bearings. Finally, overall efficiency is the ultimate ratio. It combines all volumetric, hydraulic, and mechanical losses to compare the final shaft output against the net power available at the turbine inlet. We start with static reservoir potential, route it through a frictional penstock, and strike the runner for rotation. The specific geography, the head, the specific speed, and the required fluid action determines whether an engineer specs an impulse Pelton wheel or a reaction Francis or Kaplan unit. Regardless of the design, the thermodynamic reality of volumetric, hydraulic, and mechanical losses strictly dictates the final output. Here are the critical parameters, specific speed ranges, and mathematical formulas governing these extraction systems. The modern hydraulic turbine functions as a precise intersection of fluid dynamics and mechanical design, engineered to extract the maximum energy density available from its specific landscape.